Okay, so page 4 of the 2018-2019 first session. We're still in the acid-base section, and in the following 9, 10, 11, you have the following given. 10 milliliters of a weak diacid H2A with a concentration of 10 negative 3 mol per liter. They want the pH. That's the first question that they're going to ask. Remember, you have a way to treat diacritic acid, and it consists of several steps. The first step that you do, if pKa2 is greater or equal than pKa1 plus 2, it means that you have at least a difference of 2 between pKa1 and pKa2. This 2 is because of the 100th error that we take. A few years ago, it was 1,000, so be careful what they set the error for this year. This is from the fact that if Ka1 is greater or equal than 100 Ka2, you can neglect the second acidity. If this rule is satisfied, you can neglect the second acidity. What do I mean by the second acidity? You already know that H2A will dissociate into HA minus plus H3O plus, and then HA minus will further dissociate into A2 minus plus H3O plus. Saying that you neglect the second acidity means that you choose, based on the error that you have, to neglect the action of this reaction. Basically, you study only this reaction. That's it. And since this rule is satisfied, then we will consider only the first reaction or the first dissociation in the diacritic acid, which is H2A. To calculate the pH, go with your validity. Validity states, the first rule of validity states that you can neglect the concentration of HA minus in your system when the pH is equal to half pKa1, remember, because we're working with this first acidity, minus half. Look, the initial concentration of H2A, if it is less or equal than pKa minus 1, pKa1. So if this value is less or equal than pKa1 minus 1, it means that yes, you can neglect the concentration of HO minus, and yes, your pH is that exact value. Pay attention to a very small detail. This is the concentration of H2O in your solution. Now, if you look in your solution, they said 10 milliliters of a specific concentration. They did not change the volume. It means that the concentration of H2A in your solution, in the solution that you're working with, did not change. Be careful with that trick, because when they change the volume, you have to change your concentration before you proceed. So based on this, it's half pKa1, which is 4, minus half log 10 negative 3, less or equal than, what is it? 4 minus 1 is 3. The answer of this one is 3.50. Is it less or equal than 3? No, this is not valid. It means you cannot neglect the concentration of HO minus. The concentration of HO minus in your system is substantial, خليني أقول. Since you cannot neglect it, what you do is that you move to the quadratic, which states that H3O plus squared plus Ka1 H3O plus minus Ka1 times the concentration of H2A, which is 10 to the negative 3, equals 0. Find the value of H3O plus. It will be around, I think, 2.7, negative 4 mol per liter. And then you find the pH. The pH will have to be slightly larger than this value in this case. So it's negative log this value, which is around 3.568. Look at your answers. It's rounded to 3.57. Number 10. Calculate the pH of the final solution obtained after the addition of 10 milliliters of 10-3 molar NaOH. This is basically a titration reaction. Okay, it's not titration because it's not drop by drop. Usually titration is done drop by drop so you can do the curve, but this is a complete reaction with a strong base. So it's similar. It's basically a neutralization reaction. When you have a neutralization reaction, you cannot neglect the second acidity. It depends on the value of HO minus given. So if the value of HO minus is given enough, you have to work, first of all, to neutralize the first acidity, which is H2A. And if you have enough left over of HO minus, you have to move to the second one, which is HA minus. It depends how much of NaOH you have. So what we're going to do is we're going to write H2A plus HO minus. This is basically the reaction that is happening. And whether you continue to the second reaction, which is basically HA minus plus HO minus, H2 minus and H2O, dictated by the amount of HO minus left after this reaction is finished. And pay attention to something else. Initially, you had 10 milliliters of the initial solution and you added to it 10 milliliters of the NaOH. Your volume has changed. Since the volume has changed, you either have to calculate the new concentration or work with millimole. Let's work with millimole. So H2A is basically 10 milliliters, 10 to the negative 3. I'm going to do millimole here. HO minus, again, 10 milliliters times 10 to negative 3, which is the molarity. Initially, I'm going to assume it's nothing. Both of them are equimolar. Both of them are the limiting reagents. What you get is epsilon, which is, remember, it's basically approximately 0, and 10 times 10 to the power negative 3 millimole. Because all I have in my solution is this species, which is what I call an amphoteric species because it can act as both a base and an acid, nothing else. Everything else can be neglected. I can simply say that the pH, again, go back to your validity, is equal to pKa1 plus pKa2, which is half 4 plus 8, 6. In case this is not what you have, and you have an amount left over of HO minus, you move to continue the reaction of this one. And if you need to find the concentration of HA minus, it is the millimole, 10 milliliters, 10 to negative 3, divided by the total volume, which is 20 milliliters. This is how you find the new concentration in your system. But I don't need this just for this case. ما بدي أحط X حتى ما تفتكروا إنه it's wrong. Just in this, in MCQ, don't waste your time with anything else. Just answer the question because you have very limited time. Number 11, calculate the pH of the final solution obtained after the addition of 13 ml. Gonna do this, 13 ml of NaOH. Now, you can follow this same method and try to do that. So put 13 times 10 to the power negative 3, you will find that you will have a remaining value right here. And because you have a remaining value right here, you're going to move to the second equation. The value that you will have left is basically 3 milliliters because 10 milliliters has already been consumed by H2A. And you're going to have a mixture of HA minus and A2 minus in your system. It will be in the buffer zone and you can follow Henderson-Hasselbalch. Or you can follow the titration rules that we put, the titration derivation here, basically it's the derivation that we did of how to determine the pH in terms of X. And you need to understand those derivations, because if you don't understand those derivations, you're going to make a mistake in choosing which one you have to use. But in this case, what I can say is I can define X by the volume added, which is 13 milliliters, divided the volume for the first equivalence point. The first equivalence point, since both of them have the same concentration, then to neutralize 10 ml of H2A, I'm going to need 10 ml of HO minus. So that's the first equivalence point. So it's 13 divided by 10, which is 1.3. If this is my X factor, and what I have in my system is HA minus and A2 minus, it's simple arithmetic. I know that 10 milliliter of HO minus has already completely neutralized H2A. That means what I have in my system is a mixture of HA minus and A2 minus. I am stuck in the second neutralization reaction. These are the two species that I have. pH, and again, go back to the derivations, is equal to pKa2. If you don't have them, let me know. I can do a small recording of the derivation in terms of X. It's equal to pKa2 because I am in the second one, plus log X minus 1 divided by 2 minus X. Follow this equation. pKa2 is what? 8 plus log 1.3 minus 1 divided by 2 minus 1.3, you will get your pH, which is 7.632. Very easily, without having to go through these equations that we saw in number 10. So it's 7.63. No, sorry. The second method to do this is to do the same that you did in number 10, okay? Number 12. Glycolic acid is a monoprotic acid with a pKa of 3.9. It's a monoprotic acid, so I'm simply going to do HA. A 25 milliliter solution of glycolic acid is titrated to the equivalence point with 35.8 milliliter of 0.02 sodium hydroxide. This tells you that you need 35.8 ml to actually get to the equivalence point. That's your equivalence volume. What is the pH of the resulting solution at the equivalence point? Okay, let's take it step by step. At the equivalence point, this is basically HA plus HO minus to give me A minus plus whatever. No, A minus, sorry. At the equivalence point, all I have in my solution is A minus. This is a weak base. The pH of a weak base, according to the validity, it's 7 plus half pKa plus half log the concentration of A minus in your solution. This is your pH if this value is greater or equal than pKa plus 1. I have the pKa, I have the 7. What I need is the concentration of A minus in my solution, and no, it is not this, it is not this, it is not this. We have to calculate it. And I know at equivalence point that the volume of the acid taken, which is 25, let's not write the rule because it's gonna just consume time. The volume of the solution that I have of HA, which is 25 ml, times its concentration. Okay, فعليا it's written as CHA, not within parentheses, has to be equal to the equivalence volume taken, 35.8 ml, times the concentration of the base that I use, which is 0.020 mole per liter. Then the concentration of HA is equal to 0.02864 mole per liter. This is the concentration initial of HA. Is it the same as A minus? هون السؤال. Do you think that this will be the same concentration as A minus? Now pay attention. Throughout your reaction, you do have what we call the conservation of mass, the number of mole. The number of mole has to be conserved, yes. So the initial number of mole of HA after its complete neutralization has to be equal to the number of mole of A minus after the reaction is finished. Especially that this is a complete reaction and it's complete neutralization. Number of moles will be equal, yes. Concentrations will not, because the concentration of HA was given for a 25 milliliter solution. The concentration of A minus will exist in a 25 milliliter solution and a 35.8. مش هيتبخروا الامount of A minus, the volume of HO minus اللي أنا حطيته. HO minus will disappear, it will be consumed, but it will change into H2O. So this volume will not disappear. You have a dilution factor in this case. So you have to find the new concentration of A minus, which is basically its number of mole. How do I calculate its number of mole? It's 0.02864, which is the concentration times its volume, divided by the total volume, which is 25 plus 35.8. Concentration of A minus in your system is 0.01171 mole. Then you go back 7 plus half pKa, which is 3.9, plus half log 0.01177. Is it greater or equal than 4.9? This will be a value of 7.985. It is greater than 4.9. This is valid. This is my pH. Go. خلينا نلاقي الvalue. It's basically 7.985. It's 7.99. And remember that I'm taking the long route to actually solve these exercises. You can do it very quicker, okay? Very rapidly.